Hi everyone, on today's video we're going to be having a look at setting up an external aerodynamics analysis using Altair's AccuSolve CFD solver and HyperWorks CFD 2020.1 preprocessor. So we'll be having a look at the geometry cleanup side of things and making sure that the geometry is ready to be meshed. We'll look at the boundary condition setup and simulation setup, apply some meshing conditions to the model and run the mesher, have a look at what solution settings we have before we press run on the solver, and we'll have a look at some of the results too. So let's have a look at what we can do today. So we'll go into File and Import to bring in the geometry. So go File, Import Geometry Model, and you should have this formula1.stmod file. So we'll go ahead and open that. So we do have some geometry import options, more notably the topology side, so you can edit the cleanup tolerance and target units based on what units the CAD model is in. So AccuSolve works in SI units only, so the car will need to be in meters and all your inputs will need to be in SI as well. But for this case, we'll just leave it as is for the moment and we'll import the model. So here it is. And the first thing that we should do, again, is just to check what the units are. So we can draw a line from, say, the front of the nose cone to the midpoint of the rear wing, and we can see that we've got 4.68 e to the plus 3. So this is in millimeters. So we can press Escape or right click and swipe out of the tool, and we'll need to scale it. So we can go to this little drop down by Edit and choose Scale. So we can choose the solids, which would be this part, and let's go for 0.001 and run the scale. So here we go. We can do a double check. If we right click and swipe out of that tool, go to the measure tool, and we can press the front of the nose cone to somewhere on the rear, and we can now see that we're at 4.68 meters. So we're now in the right units. Now we need to go ahead and actually clean up the model, so there may be some problems with it. So let's adjust the sliver tolerance, and we're going to apply a value that basically the number below this, the size below this, we don't really need to mesh. So we can change this to 0.003 because we don't really want to look at any sort of surfaces that are below that size. So let's press enter on that, and then left click on this validate button to actually see what problems there are within the model. So we've got 43 surface checks. So we can left click on surface checks, and we can see that we've got 41 slivers and 2 intersections. So we can click on slivers, and we can have a look. We can rotate around the model and see where they are. So say if we zoom into here, we can see that there's some odd sliver sections around here, and equally we can cycle through them using these 2 arrows. So we can run across the model and fix them. But ideally, we would just like to fix them all in one go. So we'll press Fix All, and you notice that we've gone from 41 to 32 slivers. So it's not managed to fix them all, but what we can do is we can go into File, Preferences, and then go to the Hypermesh Geometry section, change the cleanup tolerance to manual, and if we make this 0.003 like the sliver tolerance, and then press OK, we can press Fix All again, and you can see that it's now fixed all the slivers. So that's that one finished, but now we've got a couple of self-intersections. So let's have a look at the 2 intersections we have here. So you can see that they're here, so the bottom surface of the main plane of the front wing and this adjacent surface. And you can also cycle through them and it will show you what the problems are. So we're going to focus on this surface here as it's smaller and easier to repair. So the function here is to actually delete the surface. So if we just left click now that we see that tick on this surface, it'll delete it. So we can come out of this surface tool and then now go into patch using this surfaces button here and use the patch tool within that. So although it may be difficult to see, there's actually a hole in this region as we've just deleted it. So we can double click actually on just one of these edge loops because it knows there's a free edge around here. So if we double click on this, it'll actually patch that surface for us automatically. So there's that surface sorted. We can go into the surface repair tool again, and we can see that the only problem we now have, well, not really much of a problem in that it's a closed shell. So a bounding group of surfaces that isn't forming a solid body. So you can see here on the left that we have this rectangular shape indicating that this is just surfaces. So if we click on closed shells, we can then create this one solid body that we need. So we will be needing the solid body to do the Boolean subtract. later on when we make the enclosure. So that's the problems with the car geometry sorted, so we can validate that again, and that should hopefully give us a blue tick. So now that we've done that, we can then go ahead and start to create the enclosure. So the first thing that we'll do is we're going to split the car in half. So for the sake of hopefully chopping the runtime in half and the node count in half, and obviously speeding up the solve time, we're going to split the car in half and run a symmetry condition. So what we need to do here is go to the split tool, we'll go to plane, and the target we will switch to solids, and then let's choose the tool. So if we go somewhere on the car, maybe sort of at this point, and orientate the mouse such that the saw is sort of facing down the length of the car, and then left click once you're there. Because we snapped to that point at the midpoint of the car, we know that we're pretty much halfway down the car, so we can go ahead and just press split, and this will create two separate bodies. So we'll right click and swipe out of the tool, or just press the split button up here to come out of it, and you can see that we've got two bodies. So we're going to go ahead and just delete the right hand side. So you can either press delete on the keyboard, or you can right click on the solid body and just press delete. What we will do is we'll validate it again, because you can see that the blue tick that we had has gone to the exclamation mark. So if we press that, we can still see that we've got the blue tick. So now that we've chopped the car in half, we can go ahead and create the enclosure. So we'll right click and swipe out of that tool, press this solids button, and we're going to choose the box. So within here we've got a few options like free drawing or by plane, but we're going to use fit to, and we're going to change this to solids and choose the car. So you can now see that the solid has been wrapped around the car, and we'll press play on that. But now we need to actually position the enclosure in the right area, so with the bottom of the enclosure or the ground in line with the tyres, and the side of the enclosure on the symmetry side on the same plane as the symmetry of the car. So we'll come out of that tool, and the first thing that we're going to do is we're going to use the move tool to just choose this solid, and we'll drag it away. So now what we'll do is we're going to hold down shift on the keyboard, and you should see that the color will change, so the enclosure will go transparent, and then we can now move this manipulator. So if we go to the center point of the manipulator, let's snap it to the midpoint of the length and of the and online with the bottom surface of the enclosure. So now if we let go of shift, we can start clicking this around. So let's snap this in line with, say, the endpoint on the car. So you can see that the point around here is in line with the symmetry plane of the car. And another thing we can do is take the Z arrow and actually lift it up and down, but we want to snap it to the endpoint on a tyre. So now you can see that it's in line with the two tyres, so the bottom surfaces of the tyre, and also with the symmetry plane. So now that this is done, let's right click and swipe out of the move tool, and let's actually size the enclosure. So what we want to do is we want to go to the drag tool, and then let's choose this. So this is the inlet of the enclosure. We don't want to remove degenerations, and we don't want to retain the shared edges. So let's put in a value of, let's say, 10 meters. We now need to click somewhere else, so click off screen somewhere to deselect the inlet, because now we're going to focus on the side. So let's go 10 meters to the side of the car. Let's focus on the outlet region, so this will be maybe 30 meters behind the car, and then say 10 meters, repeat that to the top of the enclosure. So these sizings are going to vary depending on the application, be it for Formula Student, for example, or for Shell Eco Marathon. That's up to obviously you to perform an enclosure sensitivity study, see how far the outlet needs to be, how far the top, the sides and the inlet need to be, for example, so you can retain the fidelity of the simulation but reduce the number of nodes within the model to help you solve a little bit quicker. So now that we've created this, we actually need to subtract the solid body of the car from the enclosure, so we can leave basically a car-shaped hole within the enclosure. So we'll go to Boolean and we'll choose subtract, So the target's going to be the enclosure, the tool is going to be the car, and let's press subtract. So now that that's done, we have a car-shaped hole in our enclosure. So we need to validate it again, and we've got a couple of problems to fix. It's just a couple of self-intersections, so we can see that it's the side of the chassis and a surface on the barge board. So what we can do is we can go ahead and just left click on the barge board to delete that surface, and like before we'll come out of this surface tool and we're going to manually patch that surface. So what we can do is again come out of that tool, and we can change the selector to surfaces to make it easier to find the barge board. So you can either choose on screen, or you can press S on the keyboard to switch from solids to surfaces. So now that we're on surfaces, we'll click this bottom surface, so left click on there and just press H on the keyboard, and that will hide that bottom surface. So we can zoom into the barge board, rotate around here, and we can see that we have a hole on the back of the barge board, and like before we can go into surfaces, into the patch tool, and because it knows there's 3 edges all along the barge board, we can just double click on one of the edges and it will automatically patch that tool for you. So we can come out of that, the surface has been patched, we can press A on the keyboard to show everything again, and then finally let's validate the model. So we have one surface check, but this is likely to be the closed shell. So it's now noticed that there are a series of enclosed surfaces which can form a solid. So we'll go ahead and we will create that solid. We can then again validate it. We have the blue tick, so now we're ready to progress into the boundary condition and flow setup stage. Now that we've performed the geometry cleanup and we have the blue tick on the top right of the screen, we can then move on into the flow setup side of things. So to make life a little bit easier when it comes to the setup from here on in, so that includes for the flow setup and the meshing side of things, and even creating surface outputs if necessary. Sometimes it's nice to create groups so that everything's sort of organized, and it makes selection downstream a lot easier. So we're going to go ahead and first just with a left click and drag hide off. So select these, press H on the keyboard, hide off the outlet, the ground as well, so we can just focus on the car. So let's snap to using this button here. We can go to ZX and let's start grouping. So we have the group function here, and we're going to create a set of surface groups. So change the selector to surfaces, and then we'll just do a left click and drag around here, and that'll encapsulate all of the front wing and a couple of bits of the nose cone which we don't want. So if we press shift on the keyboard and then click and drag around here, it will then deselect those 2 surfaces. So you can now see that we're only selecting the front wing. So we'll press play to accept that, and if we right click on the surface group and go to rename, we can call it front wing or FW. So I'll hide that off now that that's been done, and now we can focus on doing the front wheel. So if we again do the same thing, we can rotate it around here, make sure we're selecting everything. So left click and drag around here. You can see that it's picked up the suspension, so we can just right click and shift and it will deselect these as well. So that's the front wheel done. Press play, rename, we can call this front wheel. Okay, we'll hide that off too. We'll add the suspension because they're likely to have differing mesh controls, so we can just click and drag these parts, make sure we selected those, so we can rename that again and hide it off. So a bit repetitive, but it does make selection a lot easier later on. So let's try the rear wheel too. Make sure that we're capturing all of the rear wheel, and anything that we don't want we'll just shift and deselect. And anything else that we do spot we can manually deselect as well, just using shift around here and around this side as well. So we can check that we've got these surfaces, and we can add using control. So if you press control you'll see a plus appear, so we need this surface, and around here. So I reckon that's all of the rear wheel. So let's press play. And rename that to rear wheel. And if you ever want to check that you have selected the right surfaces and not chosen anything else, you can right click and choose isolate. So you can see here that, yeah, we've got just the rear wheel itself. And then we can isolate the unassigned, and again that's going to bring back the surfaces for the whole enclosure. So we can just come out of group and then just hide them again and focus back on the car. So back into the group, go into the surfaces side, and let's start selecting just the rear wing. So we can choose those, these as well. Let's pick up a couple of the suspensions, so we can press shift to deselect, and same for this part too, we don't need those. And we can have a rotate around and see that there's a few missing here, so if we press Control we can just add these into the model. And I believe that will be it for the rear wing. So let's press play on that, rename that to rear wing. We can hide it off, and then really just left, we're just going to do the suspension components. So if we orientate it to this view, drag around that, you can see that we've collected most of them, and yeah, we can press play on that. Rename it, hide it off, and the rest really we can just call as the chassis. So that's the grouping done. So we can show all of these. And the rest are just going to be the enclosure. So let's come out of this, show everything again, and now let's start having a look at the physics. So everything in this tool is basically in a left to right workflow. So the first thing that we want to do is define the physics of the model, so we can either run steady state or transient with varying time stepping controls. So we'll run this in this case as steady state as it's faster. Flow wise, so either laminar or turbulent, but very likely to be in the turbulent regime, and we have a whole host of turbulence models to use as well. So now, because these are only required for steady state simulations, you're not going to see the transient turbulence models unless you initiate the transient button. So for example, you can see here that we go up to k omega. If we switch back to time and change to transient, and we go back into flow, you can see that we've got a lot more turbulence models, all the way up to large eddy simulation, for example. So HyperGraph CFD knows the buttons that you want to press beforehand. So another example is if you're running heat transfer, you won't be exposed to any of the heat transfer functions unless you explicitly turn heat transfer on. So we'll go back into time, we'll put it to steady state. Let's say shear stress transport, again this is up to you on to what turbulence model is best for your use, but in this case we'll go with SST. We don't need heat transfer in this case, there's no multi-fluid or species transport. There are some other solver controls you can change, so there's a relaxation factor in there. You can choose the maximum number of steady state steps you wish to choose, and the convergence tolerance. So AccuSolve is second order accurate in time and space. So this is why the convergence tolerance here is 1e to the minus 3, whereas in other codes you may see this as 1e to the minus 4, for example. So as standard for AccuSolve, 1e to the minus 3 is a good place to start. So that's the physics setup. We do have a material library, but you can add your own material properties as well. So again, that is up to you, and you can import them, save them out and share them around as well. So only really one person has to create the material once. But in this case, we're just going to use standard air. So we'll press on the material button, and we'll choose this solid. It's already known as air, but if you click on it, just in case it isn't, you can see that we've got a host of options for materials, but we'll just leave it as air and press play, and we'll select that. In this model, we don't have any radiators, but if you were to have a radiator, just for purely demo purposes, I'm going to throw on a porous domain just to show you how easy it is to set up. So say this is our porous domain, for example, you can choose the orientation and then apply Darcy-Forsheimer coefficients, define the permeability in different directions, or if you happen to have a velocity versus pressure drop information, you can import this and the Darcy and Forsheimer coefficients will be calculated for you. Obviously, you'll need to put in the thickness of the porous domain, the density and the viscosity of the fluid as well. So we'll delete that off as we have no porous media in this domain. And actually, one other thing to show you is that if you are going to be iterating through different models, is that we have parameters and multipliers. So you can create a parameter for the inlet condition. So for example, for a press parameter, I can say inlet. I can give it an expression, and this could be, say, 5. Or I guess 15 in our case for what will be the inlet speed. So you can use this, and I'll do this for the inlet condition in a second with the parameter manager. So now that we've done that, we now need to assign a reference frame. So in some cases, some of the easier methods of modeling wheels is to just assign a moving wall with a tangential velocity to the surface of the wheel. But in this case, we're going to apply a reference frame, whereby all the nodes around the wheel are going to be solved around that reference frame. So in this case, let's left click and hide off the enclosure. And in this case, because there's a surface within here, we need to assign a point in which to assign the axis of the reference frame. So we can go into the Geometry tab again, go to Create, press Create Points, and we can go ahead and find the center point of this wheel. So we can assign one there, and let's do the same for the rear of the car, just clicking and it will identify the center, and then click again. So there is our center point of the wheel. So we'll right click and swipe out of that, go back into Flow, and let's choose the reference frame. So the wheels are actually surfaces, so we're going to change this selected to surfaces, and now we'll have a look at the point of creating groups. So using these 3 dots here, we can bring up an advanced selection tab and go to by group, and in this case we're going to choose the front wheel. So now it's selected all the surfaces of the front wheel. We will come out of this and go to axis, and we can choose this center point here. So we want to align it now to the y-axis, and you can see that the rotation is the wrong way around, so we can just flip that and put in the rotational speed. This is going to be in radians per second, so for this radius of tire and speed of 15 meters per second, it's going to be 49.2 radians per second. So we'll press play on that. We can rename it again just to reference frame front, and we need to do the exact same for the rear. So again, same process, switch to surfaces, press the 3 dots, we can go to by group, and let's choose rear wheel and come out of that. We'll choose the axis, which is the center point of the wheel, and we want to put the axis to Y, switch the direction and put in 42.9 radians per second. So let's press play on that one, and we can rename this again to reference frame rear. Okay, so now that that is done, we can actually go ahead and assign the boundary conditions for the model. So press A on the keyboard again to bring everything back, and let's start creating the boundary conditions of the model. So the first one we can do is the inlet, so we'll press constant in this case. Nothing has been assigned. There is a default wall function which by standard will just run as a no-slip wall, so technically speaking you don't need to assign it, but it's nice to assign certain conditions like front wing and rear wing rather than just leaving them as default wall, because you'll get specific surface outputs. So if you're looking at the performance of the front wing or the rear wing, it's nice to have the separate surface output for that, so that you can take the data from that and see how well it's performing. So looking at the inlet condition, we've pressed constant. All we need to do is left click on this face and choose the inflow type and switch that to normal, and we can put the normal velocity as either 15, but we set a parameter earlier called inlet, so if we start typing inlet, it will bring up inlet for us, and we can just click it, and that will assign 15 meters per second to this inlet condition. So if you were to go back and change that parameter, so you want to look at a different inlet condition, you could just change the parameter rather than having to change this every single time. So we'll create the inlet, and we can hide it off now that we've done it, we need to create some slip walls. So let's go to slip condition. So this is going to be the top and the side of the enclosure. So we'll press play on that and we'll hide that off. We have an outlet, which is going to be this one, and we'll leave the outlet static pressure as 0. Let's hide that off too. We have a symmetry condition, which is going to be this wall, and we have the ground. So the ground is going to be a moving wall because obviously it's moving at 15 meters per second. So we can choose a Cartesian type in this case, and it's going to be positive 15 meters per second. We'll press play on that. And then we're going to create the individual surface outputs. So even though these are all no-slip walls, like I mentioned, if we want surface outputs, it's better to either create the boundary condition for them, or you can set surface outputs before you run the solver. I tend to just create the surface outputs or set the boundary condition so that I have the surface outputs for different parts. But it's quite easy. We can go to the no-slip wall condition here, and like we did before, we can just use these 3 dots here to choose the groups. So let's say still with the front wing, and then we can come out of that and just press play, and we'll name that again to front wing. And this will be handy for meshing downstream because we can take boundaries from the meshing side to apply the meshing controls to. So we've done the front wing. We'll change that to group again. So rear wing. If you press the middle mouse button down, it'll actually accept that action. So that might be another way, a swifter way to move through. So we can go into group again, and it's created another wall. Let's try the front wheel and press the middle mouse button to accept, or if not, we can just come out of this and press the play button. Do the same for the rear wheel. And whatever is left within the model. So we've got the front suspension to do. Rear suspension as well. And then I believe just the chassis. So we'll assign the chassis. And again, for the sake of the surface outputs, we'll rename them. Otherwise, you're just going to see wall 2, wall 3, and it may not make much sense. So we can isolate the ones that we haven't named. So in this case, this wall is going to be the ground. This is the rear wing. And let's show the other wheel as well. So wall 2 is going to be the front wheel. This will be the rear wheel. The front suspension. The rear suspension. And finally the chassis. So that is about it for the boundary condition setup. Now that that's all finished, other things that we can do, again for slightly more complex simulations, is there is a level of mesh motion within here. So we can either fully specify the mesh motion or use an arbitrary Lagrangian Eulerian mesh motion approach, which calculates what the mesh deformation should be for you. And for example, you could do this for things like activating DRS. So rather than sweeping through different angles of attack as the DRS is actuated, you can transiently model this using a rotational function within here. That involves a slightly more complex mesh setup, so we're not going to focus on that today, because again, it's going to increase your runtime by quite a lot. So now we can consider moving on to the meshing side of things. Now we can move on to the meshing side of things. So let's move on to the mesh ribbon, and we'll start applying some surface controls, some boundary layer controls, and then we'll run the main meshing. So let's enter the surface control by left clicking on it, and again we're going to use the 3 dots here to run through the boundaries that have been created beforehand. So in this case we want to select the front wing, and we'll we'll use the rear wing as well. They'll have similar sizing. So we can change the sizing to, in this case, let's say 0.01 meters with a geometric feature angle of 15 degrees to capture curvature a little bit better. So we'll press play on that one, and again for organization we can just call this wings if we ever want to edit it later on. Another thing that we can do, again for just visualization, we can hide off these surfaces to see what's being selected. So let's zoom into the car, and now let's focus on the suspension. So using this tool again, with the by boundaries in the advanced selection box, we can choose the front and rear suspension. And we'll change this value to about 5 mil, and again a 15 degree geometric feature angle. And we'll rename that to suspension. Next thing is the wheels. So let's choose the front and rear wheels. Give these a sizing of 0.01 and again 15. Renaming that to wheels. And then the chassis. So obviously this is quite a large part of the car, so we're going to roll with a value of 0.05 meters. So there's the surface sizing for the car covered. We'll now focus on the boundary layer sizing. So here we're going to apply one for both the car, and actually in this case we're going to include the ground as well. So if I hide off these surfaces, now typically what you'd actually do is calculate, say, a first layer height condition for the ground, for the front wing, for the rear wing, for the wheels. They're all going to be different, and they're going to be based off the Reynolds number and the Y plus value that you're looking to use. So this will be dependent on things like the turbulence model or the level of accuracy that you're looking to achieve. But for this case, as it's just a demo model, I've considered a Y plus of 30, and my Reynolds number is based on the length of the car and obviously the material properties of air. So in this case, just for simplicity, I'm going to create a boundary layer on all of these components just by a click and drag. I'm going to set the first layer thickness definition to about 0.008. So this is for Y plus of 30. I'll give it a total number of layers of 12 with a constant growth rate of 1.3. Now, some of the things that you want to look at once the mesh has been created is that there is a smooth transition from your boundary layer mesh to your volume mesh. So you can go ahead and edit these settings. This is what I've looked at to try and get something that looks reasonably decent. Obviously it doesn't come out right first time for you on whatever model you're looking at, whatever Formula Student, Shelley Marathon car it may be. Just ensure that there's a decent transition from boundary layer to volume mesh, so that basically the sizes between the two aren't too different. Naturally the volume mesh will be a little bit bigger than the boundary layer mesh. So we'll apply that, and that's our boundary layer control done. In this case, I'm not going to apply a volume mesh because the batch mesher is really going to take care of that for us. But if we had loads and loads of volumes in here that needed a final refinement, we would do that, but we've only got the volume of the enclosure here. So what we'll do instead is we're actually going to apply a refinement zone behind the car. So using this refinement tool here, I'm going to go ahead and just drop this at some point on the car so that it's in line with it, and then click and drag to a certain size. So now what we can go ahead and do is actually position this around the car region. So if we move that across, we can move the manipulator again, and so using shift we can move the manipulator, and then if we not holding shift anymore, just snap that to sort of the surface center of the car, we can begin to position this correctly. So if I left click on the face and then left click again, I can see that this extrude button comes up, so I can just drag the refinement zone just somewhere in front of the car, and we'll do the same for the side. So we'll just extend that beyond the car slightly. We will go behind the car quite a bit, so obviously this is going to be highly turbulent behind the car, and we want to try and resolve those flow features as best as we can without using too much computational requirement. So we'll use this refinement zone into the region where we expect there to be wake, which is going to be quite far behind the car, and equally above as well based on the upwash. So we can raise this to about maybe 4 meters. So just as an example, and again it's for you to have a look in the post-processing side of things, having a look at the results and making sure that there isn't any mesh dependency on the flow features. So if you do see that, you'll want to start refining the mesh further in those regions. So there is the refinement zone done. Obviously, if we double click on the size, we don't really want a 10 meter refinement zone because that's not going to help us too much. So let's make this 0.1 meters. And then we can right click, swipe out of that, and there is our refinement zone created. Press A again to bring everything back, and one of the last things that we'll do is we'll actually batch mesh it. So there are some local interactive controls that you can use. So this will apply a surface mesh first, and you can keep that when you do the batch mesher, but that's only for sort of local surface meshing. And there are other things like edge controls, gaps when surfaces are coming within close proximity, and angle refinements that you can apply. But in this case, we're going to press the batch mesher. We'll choose an average size of about 0.75 meters, and we can leave the rest as is, and we'll just press mesh. It does take about sort of anywhere between 5 to 10 minutes, depending on the power of your computer. So I'll bring up the finished mesh now. So once the meshing is complete, you'll see that this button here, so the visualization view, will now show a mesh, and if we just zoom in a little bit, you can now see that we have the mesh within the model. So we can perform a cut section on this. So I have one in here, but let's just create one from scratch. So if it appears like this, we can swap the side of the section cut and we can actually manipulate it. So what you may notice is that the tool may snap to certain parts. So if it snaps, what you can do is hold down Alt on the keyboard, and then you can click and drag freely. So let's click and drag with still holding down Alt to some point along the car. So let's say around here, and we can let go, and then let's zoom in, and we can see the refined mesh that we have around the car itself. And we can take a look at a closer look at the boundary layer, so you can see that there's sort of a smooth transition from the last boundary layer element to the first volume mesh around here. So we can check, see if the mesh is looking decent around the car, and then that's about it. We can have a look at, so if we escape out of this, so we'll come out of the section cut, just pressing escape or right clicking and swiping out, we can go back to just the geometry only view. And if you want to see how many nodes are in the model, so if you go towards the measure tool and you press the entity count, you should see in here firstly how many points, lines, surfaces are in the model, but also nodes. So in this case we've got 3.362 million elements, or nodes, sorry, within this model. So AccuSolve does work off node based, so the size of the model really in this case is based on number of nodes. So here we have just over 3 million nodes. And we can move on to the solution side of things. So now that the mesh is done, we're pretty much ready to go. So if you haven't created sort of the different surface outputs that you want, you can do them here. So because we did them in the flow side of things with the boundary conditions that we set, we're going to have all the surface outputs for all the boundary conditions that we created. So front wing, rear wing, suspension, etc. If you didn't do that, you can do that here as well. And it's again pretty easy. You just select one of them, click on the surface, choose how often you want the information, and press play. Actually, we don't want to do that because we already have the inlet condition, but that's something that you can do. When it comes to actually getting the data, so for example, if you want data every sort of 50, 100, 150 time steps, etc., you can assign that within here using this function, so the time step interval here. And again, another thing we can do is initialize the solution, so basically giving it an easier first guess when it comes to the iterative solver, so it can basically get to your answer quicker. So for example, we've got 15 meters per second going in the x direction of the model, and it's likely to be the case all over. So what we can do is press the part condition, click on the solid body, press the plus, and let's say we want x velocity, click into the box and change that value to 15. So that will give all the nodes within the model condition of 15 meters per second in the x direction, which is sort of close-ish for a large amount of the domain as to what the values at those nodes should actually be. So we can press play on that, we'll take out of that, and then we can go to the run side of things. So within here, obviously you can give a problem name, choose where the files are to be saved as, choose which processes, so be it just the prep side or the solving side, or obviously both. And one thing that I would recommend is to change the parallel processing to Intel MPI and then just throw as many processes as you have to the model, as it's obviously just going to help you solve a little bit quicker. There are some default initial conditions that you can set here as well if you don't set any initializations there either. Not that you have to do them, it's just a way to sort of help the solver converge a bit quicker. Equally, if you, for example, had access to a cluster, we have the file export solverdenk function. So this will print out an AccuSolve input file with the mesh that you can take to a cluster and solve for even faster speed-up times. And that's it. So the solver will run. Again, it's really dependent on the amount of cores that you have, so I can't really put a number to that. It's an example on mine for sort of 32 cores. It took somewhat around 45 minutes to an hour. And AccuSolve is pretty linear with how it scales. So if you have half the number of cores, it's going to take twice as long to solve. So to not bring that in here, I'm going to make some results magically appear in a second. So once the model's been run, we can now have a look at some of the results. So to bring those in, we can go to File, Open, Results, and in the Run folder, you should see a .log file. So double click on that, and that will go ahead and load the results into the post side of HyperWorks CFD. So using the same controls as before, we can now see that we have the enclosure with the car within, and we can now start querying the results. So one of the first things we'll do is let's isolate the symmetry, and then we can go ahead and right click on it and press edit. So let's plot a pressure plot, for example, on this. So we can include a legend as well and edit some of the legend functions. So we can plot this in the upper right corner, choose the color map. So I'm going to choose just rainbow uniform, and we can edit the values that we see as well. So let's go from minus 150 to 150. And then we can snap to the ZX view, and obviously we can interrogate and have a look around the car, look for things like stagnation points, obviously areas which are likely to cause a lot of drag and where there's separation, and have a look at how the wings are performing as well. And we can change this easily by going to, say, velocity, for example, and we have 0 between 36, and again we can see the velocity around the car, and obviously more notably areas of separation behind the car too, and we can see the wake beyond the car. Another thing that we can do here, so if we turn off the display of the velocity vector, so we'll turn that off, and we can then apply a vector display. So let's display the velocity around the car. We want to change this to, let's say, uniform, and for a size of 0.05. So then we can have a look in, change the color to velocity, and we can turn on the legend to edit some of the values. But we can have a look around the car, look at some of the vectors, again, find points of separation and recirculation around the top of the airbox, for example, behind the wings, and again, behind the car as well. So that's a quick look just on the symmetry side of things. So we'll exit out of that. And what we can do again is just turn the display back to constant. So we can turn that off and display this as constant. And then we can turn off all the flow boundaries, then turn them all on again. Now we're going to try and create a slice plane. So create a slice plane here in this direction, and we can move it around using a manipulator function, and let's bring that sort of halfway along the car, for example, somewhere around here, and we'll just press slice. So if we hide off all the flow boundaries, we're left with just this slice plane, and we can show again, let's say, pressure. We'll change the color map to rainbow uniform, and the values again to minus 150, and tab across to go to the next value and 150, and again we can have a look at the contour and create a series of slice planes up and down the model and in any direction. Another thing we'll do, so if we hide off the slice plane and let's bring back what we can see from the car, is an ISO. So let's create an ISO surface of, we'll go for velocity at a value of 10 meters per second, and we can calculate that. So again here, this is sort of a lower velocity than that of inlet, so we can see areas that are, or that have lost energy, sort of indicating a level of separation, and we can interrogate around and sort of capture some form of vortex structures here as well behind the car. So you can have a play with the ISO value to make things a little bit clearer. Let's hide off the ISO just by clicking this button here, and let's create a streamline. So to create the streamline, we'll choose the rectangle function, and we'll choose this plane again, and we'll move it somewhere just in front of the car. So yeah, let's say somewhere around there, and then we'll have to draw a rectangle around the region that we want. So let's say around that size, and we'll choose a structured generation method, and let's put in around 40 seeds, and let's calculate that streamline. So again, we can display this as velocity, for example. We can include a legend as well, and now see some streamlines going around the car. And obviously the more streamlines you apply, or smaller rectangle, the more definition that we can get. And the same can be done for surface streamlines too, so using a similar method. So finally we'll turn those off, and now let's start to gather some data from the car as well. So we can come out of the streamline tool and go to the integration side of things, and let's have a look at, say, front wing value. So we can calculate some figures from the front wing. So in this case we have things like pressure, and we can assess the Y plus as well, so you can see that it's around 1. So we have the average pressure over the front wing, and obviously this is based on the global coordinate system too. And we can do the same for things like the rear wing. We can calculate it and see the values here as well. So you can see in this case the rear wing is creating downforce as opposed to the front wing, which is creating lift, which normally isn't necessarily what you would like. Other things that, again, you'd like to take values from is actually the force values themselves. So what we can do for that at the moment is to open up HyperGraph. So if you go ahead and find HyperGraph within your install. Once HyperGraph is open, we'll go ahead and I'm going to find my shortcut to the results, and again, like before, we'll open up the log file. So once the log file is in, it actually will load all the results, and there's plenty to query, things like mass flux. So again, you could always do a check for the inlet and outlet and make sure that the mass coming in is equal to the mass going out. But here we can see things like traction moment, velocity values, pressure values, eddy viscosity, surface Y plus, total pressure is in here as well. So plenty of functions to access. But in this case, we'll just have a look at traction, and in this case we're going to go for the rear wing, and we'll look at the Z traction. So here you can see that it's around a value of, let's say, minus 18.5 or so. What we can do is actually use this function here, the coordinate info, and go right to the last time step and see that it's around minus 18 newtons. What you can see here is that there is sort of a little oscillation on the rear wing, and based on looking at the convergence criteria and the solution ratio of the simulation, you can actually see that there's quite a lot of turbulence coming off the rear of the car, and this is a highly transient phenomena, and trying to model that in a steady state fashion can be particularly difficult, hence why you see changes in the values here. So one way to go ahead and resolve that is to run a transient simulation, which will run a little bit longer, but you'll see that the surface outputs will either sort of smoothen out or oscillate, and you can take a time averaged value for those, for the forces, the pressures, whatever they may be. So let's do the same for the front wing. Plot the Z traction. Actually, you can see here that it's making a little bit of lift, which may be what the designer wanted, but either way, we can query the values from here as well using the same coordinate info button and going to the last time step when it comes to a steady state run, and you can see that it makes 14.8 newtons of downforce. So yeah, that is a way that we could go ahead and have a look at results using HyperGraph and HyperWorks CFD post as well. Now, the final thing that I'd like to cover, which I will shortly, is the template manager, because obviously we've run through a lot of setup today, and there is a way where we can speed it up quite a bit. So we've run through all of the simulation setup and we've had a look at some results, but when it comes to the simulation setup itself and the geometry cleanup and the assigning mesh conditions to the model, obviously that required a bit of time, but we can actually use something within HyperWorks CFD to help speed that along, and that is the template manager. So within the home region we have the template manager. Now what this will do is, upon creating some groups, we can actually perform functions on those groups, so things like geometry cleanup, boundary condition assignment, assigning materials, assigning the mesh controls, and once we've done that we can actually submit to the solver. So all that means is that you can run through the setup once, create your template once, then save the template, share it around, and even rerun that template on your own machine so that you can bring in some new geometry, either perform the cleanup within or perform the cleanup manually, then run the rest of the template so that you're not setting up the simulation every single time and the meshing and solving. It's just all done automatically for you. So I'm just going to run through a brief example now of some of the things that you can do. So the first thing that we need to do is assign some metadata for the template manager to know what it's looking for. So I'm going to again focus just really on the front wing and rear wing. So in this case, let's go to a side-on view, and let's choose the front wing again, and deselect the nose cone. So here, I'm just going to right-click on the selected surfaces of the front wing and go to Assign Metadata. So I'll give it a key of tag and just a simple value of front wing, and we'll create that. We'll then do the same for the rear wing. So we'll take a sort of a top view, and highlight most of the rear wing and deselect any surfaces that we don't want to bring with us. So again, let's take these away, go beneath, get rid of these as well, and ensure that we're selecting the bottom part too. So once we've done that and we have the rear wing selected, we'll just right click on that, go to Assign Metadata, and we'll change this to rear wing. So I'm only going to perform these functions just on the front and rear wing, but you can do the exact same to the rest of the car like we did before. So for the wheels, for the suspension, the inlets, the outlets, maybe we'll do that as well. So let's just assign the metadata for this inlet, and that'll do. So now that we've done that, we need to go ahead and go back into the template manager, and we'll create some groups. So the first group name is going to be the front wing. It's a surface by metadata. The key was tag and the value was front wing. So we can press tab and put in the value again. So we'll do the same thing for the rear wing. The key was tag and the value was rear wing. And finally we'll do it for the inlet. And the value for that was inlet. We will need to also create a group for the solid body so we can select the material. So this can just be air as the group name, and we're going to change this to by part name, and the part name is solid body _2 _1, like you can see in the part browser on the left. Okay. So now that we've done that, we can perform some operations, so some cleanup operations. For example, in here we can choose any of these functions, but in this case we're going to ignore that, and we'll go to boundaries. So we need to add constant inlet, and we have a couple of no-slip walls. So this name is going to be, we'll just call it inlet. The group selection is going to be the inlet condition, and we can choose the definition here. So again, we can make that normal, and we'll give that a speed of 15 meters per second. To come out of this dialog box, just press escape. We also have the front wing, so we'll give that a name, and that's going to be the front wing. And then this is just a no-slip wall, and we're going to use the wall function as the wall treatment. We need to add one more no-slip wall for the rear wing, and we'll assign that, and again that's just a no-slip wall. And you can do the exact same for the slip walls, for the symmetry condition, for the outlet. You just need to assign their metadata before you do this. The material assignment we need to do, so we'll make that air, and the solid group name is going to be air itself, and we can apply some mesh controls if we were going to perform the meshing too. But in this case, we're just going to validate the model with a sliver surface threshold of 0.003 like before, if need be, and we're going to do the simulation setup. So we'll press run, and if we come out of this, just to check, we can go into flow. We can see that material is air, although it's typically going to be air like default, but we can go ahead and see that we have our constant inlet of 15 meters per second, and we have the two no-slip walls of front wing and rear wing based on the metadata that was assigned. So saving that template, so if I come out of this, and we'll just show everything again, you can save this template and rerun the template every single time. So include your mesh controls. Obviously you've got your meshing conditions here that you can choose using this gear button, and even submitting the solver run. So you can choose the number of cores, and just by saving this template and rerunning the template just by reopening it, you can massively speed up your solver time, because you only need to do what I've just done once, save the template and rerun it every single time. And that's it. I hope you enjoyed the video, and good luck with performing the external aero simulations with Altair's AccuSolve and HyperWorks CFD. Thank you.